Hello there. Let's talk about how your CPU fetches, decodes, and executes instructions. We're going to just do a quick surface level overview, but I hope you like it. Okay, so for starters, your CPU has something called the clock. If you see this graph right here, whoops, I forgot to keep my pen onto one monitor here. Let me just double check that real fast. Okay, is it working? Yeah. Okay, so, okay. So notice how we have this line that goes up and down and up and down. It kind of looks like a little binary line. It actually is. Sometimes your CPU is outputting a 0 to this special circuit that we call the clock, and sometimes it's outputting a 1. And it just oscillates between 0 and 1 constantly. It goes 0, 1, 0, 1, 0, 1. It does so very, 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 very fast. And the reason it does that is because something needs to control the timing of your CPU. Imagine this, we kind of take this for granted, but when you apply electricity somewhere, as a human, you kind of feel like the electricity goes to the other place, like on the other side of your house or your room or whatever. You kind of feel like it goes there instantaneously because it's really fast. But in reality, electricity doesn't go faster than the speed of light. So there is a limit, which means if you have a CPU that is executing instructions really, 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 really fast, fetching instructions from your system RAM really, really fast, there's the problem of trying to know for sure that the electricity actually made it to the other place in time. So like, what if we said, let's load some instructions from memory. They come down the wire to your CPU. How do we know when it actually finished coming down the wire to the CPU? We just take it for granted. But in reality, physics has a limit, and so the electricity needs time to get there, and it needs time to stabilize. So the clock cycle helps us with that timing. So, if we make the clock go too fast, your CPU becomes unstable. You gamers probably know that. If we make it too slow, then it'll work, but we're not getting the fastest CPU that we can. We're not getting all the performance out of it that we can. So we make the clock cycle go as fast as we can without making the CPU unstable. And so just keep that in mind. That's one component of the CPU. Okay. So then the next thing I wanted to show you, oh, and by the way, let me give credit to the authors of this book. I'm just looking at a diagram, but this book is written by someone named Kip Irvine, and it's titled Assembly Language for x86 Processors. It's written by Pearson, or it's published by Pearson, and the year is 2014, so get a copy of this book. Anyway, so this is a simplified CPU block diagram. Let me get my notes here real fast so I don't forget what I was supposed to say. Clock ticks and the ALU. Okay, so I guess that's pretty much it. So imagine now that we have a little RAM stick or some place where we can get instructions for the CPU. So this is like system RAM, we'll say. And we'll just pretend for the sake of argument that we already have existing circuitry that will easily transfer data back and forth from the RAM stick to the CPU. So anytime the CPU wants to grab some kind of data or like an instruction or something off the RAM stick, it can just do it. And that's the arrow right there. So the first thing that we should keep in mind after that is that there is a special register in the CPU called the instruction pointer, RIP in x86-64 assembly. The RIP register. And the RIP register, it basically just holds a memory location telling the CPU where's the address of the next instruction that we want to execute. So, imagine you have like some kind of memory address, 0x, I don't know, 55, and then you wanted to execute an instruction on the very next, actually let's do 50, so I can increase this by 8 without doing hex in my head. We'll say this is like the address 50 in hexadecimal. So that means that the next time the CPU wants to execute an instruction, it's just going to ask system RAM for that address. System RAM is going to give it whatever ones and zeros it has, and then it can be decoded and executed after that. And then, of course, we have to execute a program, step by step. We have to execute more instructions, and we can't just do one instruction. So typically in a program, you execute instructions one by one by one by one by one. And then every once in a while, there might be some decision logic, like you have an if-else branch. Like let's say you know, for the high level people, I'll put a question mark here. You have like an if statement, and you say like, if that's true, then execute this. Maybe I'll put this in as a green line. Otherwise, if it's not true, then we'll just execute this other logic down here. So, you know, very often we execute instructions sequentially, but every once in a while we have to jump, right? Because if you executed this if statement and you realized that this condition was not true, then you could not execute the body that came right after the comparison instructions. You would have to jump down to wherever the else block is. So there is circuitry inside of the CPU that allows you to either increase the instruction pointer by 8 bytes because 64 bits per instruction, because that's your CPU. So you just kind of go sequentially, or to jump somewhere because you made a decision, or you're like making a function call or whatever. So just keep in mind that under the hood, under this diagram, there is a lot more logic, even than the more detailed diagrams that you can find elsewhere. There's just like a lot more detail. So anyway, the RIP register just kind of increases by 8 every time we execute an instruction. Sometimes it'll drastically change its address so we can jump execution somewhere else in order to make a decision. So just keep that in mind. So suppose that we just fetched an instruction from memory. You know, it comes in here, and you know, we kind of send it down the line. We first give it to the code cache unit. Your CPU is just not a solid block of stuff. It's got, you know, subunits inside of it, and one of these units is the code cache unit. It's a lot more complicated than what you're seeing here, but basically, system RAM is very slow. Dealing with the CPU internally is very, very, very fast in comparison. So if we have like a register or some unit that we're accessing that's inside of the CPU, it's lightning fast compared to accessing the memory. So that means CPUs have caches, which just, I'm not going to go too much into caches for this video, but basically, every time we get a new instruction, we might put it into the cache, which is like incredibly fast because it's hardware that's part of the CPU. Then maybe sometime in the future, we might want to execute the same exact instruction at the same exact address again. That's possible. Remember, we have loops. We can execute the same instructions a bunch of times in a row. So if we come across an instruction that we have executed in the past and it's already in the code cache, then we don't actually need to wait for memory to fetch the instruction for us. We can just go directly to the code cache, and it's a dramatic speed up. Remember, when you access memory, execution has to stall for quite a long time usually, or sometimes. Okay, so that's what the code cache does. Once the memory and the code cache have figured out, okay, we got the instruction, everything's good, then we just sort of decode the instruction. We decide, you know, what is in the instruction? Is this 64 bits? Is it all like data, or is it all like is it half and half, and part instruction, part data, part whatever? There's lots of different formats for instructions. So the instruction decoder just sort of like, you know, decides how to separate it, and it sends data into the control unit. Notice how there's a little arrow pointing from the instruction decoder to the instruction pointer. So we could use that information to decide how to modify the RIP register, like if we're going to go sequentially or if we're going to jump somewhere. And then let's see, when we send the instruction to the control unit is not necessarily the brain, because the whole CPU is the brain of the computer, but the control unit is kind of like the decider of the CPU. At least that's the way I see it. It decides what to do. There's a lot of other subunits in the CPU. Notice how down here we have, you know, CPU registers, and we also have the ALU. The ALU is basically the arithmetic logical unit. So it's a little subunit that will execute mathematical instructions or logical instructions. Like it'll take some bits and it'll move them to the left or to the right, or it'll flip the bits or whatever, or it'll add two numbers together. The registers, you know, they're very, very, very fast. They're like, you know, the variables of the CPU. So the control unit will examine whatever it's getting, and it'll decide, all right, what does this instruction want us to do? It wants us to add two integers together, or it wants us to write something to memory, or it wants us to do whatever, right? So when the control unit receives input, remember, this is all just like ones and zeros, right? So imagine if we had like a bunch of ones and zeros coming in, and they're just wired directly into the control unit, right? So then the control unit has its own internal circuitry that makes it so, well, if I receive this number, then I'm going to tell everybody else to add numbers together. And if I see some other number, I'm going to tell everybody else to multiply numbers together. So the control unit is really responsible for deciding what the other units need to do in order to accomplish the current instruction. So, gosh, I really need to fix this. I just reconfigured this thing, and now it's just like drawing even when I don't want it to draw. So the control unit, let's say that we have like an addition instruction. We want to add two registers together. The control unit will send this down the wire to let the ALU unit know that it needs to perform addition. The ALU unit also has inputs, and based on what it receives, it will decide to do something. It'll decide to add or subtract or multiply or just whatever. So the control unit sends the right input into the ALU unit so that it knows to add or do whatever we wanted it to do. And the ALU unit also receives the operands, like it might receive data that just came from memory, it might receive registers, it might receive just like a raw immediate number that's embedded into the instruction. On the other hand, we might also send something into the floating point unit. So the control unit, it's always sending all of these signals to all of its connected units. These wires, it's not like we can remove these wires. So there's always something, even if it's a zero going down the line. So the control unit will basically send the right signals down to the ALU to tell it you're going to add, and it'll send the right signals down to the floating point unit to say you're not going to do anything, or just we're going to ignore the result. There's like all these logical gates that we're not showing on this diagram where we can just like ignore the output result of some unit that we're not going to use. So it's sending all these signals to these units so these units can know what to do. Just like a quick note here, the ALU only deals with integer math and bitwise logical operations. Floating point numbers in the machine are stored totally differently than integers, so we need a totally different unit in order to process them. So that's why there are two units there. Well, I mean, I guess depending on what CPU we're talking about, but like as far as the ones that I'm aware of and that I use. So then, the data cache, kind of the same thing. There's like a code cache up here and a data cache down there. So sometimes we might want to fetch data that we've already fetched before, and we don't want to hit system RAM. So, we don't want that slowdown. So we'll just take it from the cache. And we will also populate the cache when we have a result. So when this like ALU is done adding whatever it's going to add, it'll send its result data to the data cache. And then, like on the next clock cycle or 2 or 3 or whatever, then we can reuse the result in another instruction or send it back to memory or do whatever we want to. So this is like a basic idea, right? Like you start off by, grabbing something from memory. Possibly, if it's already in the cache, then you wouldn't actually grab it. And then the instruction decoder decides, are we gonna jump? Are we gonna go to the next instruction after this is over? So it'll have the next address prepared. Notice how there's kind of like a little cycle that goes here between code cache, instruction decoder, and instruction pointer. And so, we're always kind of deciding what's the next instruction that we're going to execute. And then we send the decoded instruction to the control unit. The control unit decides, are you going to do some addition? Are we going to use registers or not? And then, are you not going to do anything, or maybe you are going to do something? In this case, I'm just saying the floating point won't do anything if we're going to add integers. And then once that is all processed, it comes to the data cache, and we can basically just write it back to memory. I think this diagram is not showing an arrow that will write it back to memory. Yeah, the code cache is definitely not going to feed directly into memory. That's just a cache. But so imagine like there's like another wire here that goes to system RAM. So when we have a result, we can just write it into system RAM. Let me see if I forgot to say anything. RIP. Yeah, that's basically all I wanted to say. Okay, so now you have a fairly good idea of at least one level deeper of what's going on inside of your computer, how the CPU in a general way loads instructions from system RAM and decodes them, and all these little subunits getting told what to do and the results getting piped back to the instruction pointer and also to system RAM and so forth. And it just keeps going like this again and again and again. And also just remember that at certain points during even one cycle, we wait for a clock tick. I'm not going to say exactly when we wait because it's kind of specific to what's going on. It's beyond the scope of this video. But Yeah, the clock speed controls how fast these cycles go. And there's much more advanced stuff that you could learn later, like pipelining and such to increase efficiency. But this is a basic idea of how your computer works. I hope you enjoyed this video. I hope you learned a little bit of stuff and had a little bit of fun. I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.